Welcome to the materials for the sixth session in this mass spectrometry course, and this is the third and final session looking at quadrupoles and ion traps. Towards the end of the last session, we started looking at how the quadrupole trapping well depth affects quadrupole sensitivity across the mass range. And now we're going to look at some of the other effects that the trapping well depth causes. So it's probably worth reminding ourselves what this trapping well depth is. As ions oscillate down the length of a quadrupole, or as they're trapped inside an ion trap, there must be some force which is causing that trapping. So we call that the effective trapping potential, or the potential well. The greater that force, or if you'd like to think about it the other way, the deeper the trapping well, the more ions can be trapped. So how can we work out how deep that trapping well is? One measure of the strength of gravity on Earth, that is the depth of our gravitational well, is to keep throwing objects in the air at faster and faster speeds until you find the speed beyond which nothing comes back down again. This is known as the escape velocity. And we can use the same approach to find the trapping well depth in quadrupoles. To do this, we build a model of our quadrupole mass filter or ion trap in an ion trajectory modelling package. Then we create ions at the centre of that trap and fire them outwards with increasing energy until we find the maximum energy we can give ions and yet have them still remain trapped within the quadrupole field. And because in the model we have full control over all the parameters, for example the A and Q value, we can find how this trapping well depth varies across the whole of the stability region. And that's what I'm showing here. You can see the shape of the stability region, and the colour axis shows you the depth of the trapping well at a particular point. So you can see the trapping well depth for ions is deepest right down on the Q-axis at a value of about 0.6. And unsurprisingly, the trapping well depth is 0 in the unstable regions. And this figure is showing the trapping well depth for a quadrupole mass filter. So let's have a look and see what happens if we put a scan line on here. So as you recall, when used as a quadrupole mass filter, the scan line passes through the very tip of the stable region. And up at the tip you can see that the trapping well depth is very much lower than it was down on the Q-axis, where we might be using the quadrupole, for example, in a linear ion trap, or as an RF-only ion guide. Now if we were to reduce the resolution of this quadrupole, that would simply mean changing the angle of the scan line so that it passes through a thicker part of the tip of the stability diagram. But you can see that will also involve increasing the trapping well depth that ions see as they pass through that quadrupole. So what effect will this have on the sensitivity? The sensitivity of quadrupoles varies approximately by the square of the trapping well depth. So if you're using a quadrupole mass filter based device and you need more sensitivity, then you can trade off resolution to gain this. But if you go too far in that direction, you'll no longer have the resolution to tell apart different analytes, so it's always a compromise that you've got to consider. Now if we're using a linear quadrupole in RF-only mode, for example as an ion guide or in a 2D ion trap, that means all the ions will be on the Q-axis. Now here I've plotted how the trapping well depth varies as we move along that Q-axis up to the stability boundary. The well depth is deepest about a Q value of 0.6, and it drops to 0 at both the high and low values of Q. Now remember, Q is inversely related to the mass to charge ratio of the ions. So if the well depth varies for different values of Q, that means the well depth also varies for different mass to charge ratios of ions. And this then goes on to have a profound effect on the sensitivity of different ions going through the same quadrupole if they have different mass to charge ratios. So imagine we have coming from our ion source an ion beam containing the signals of 9 different ions, all with identical intensities, and all which happen to be equally spaced in the Q dimension. Now remember that the sensitivity of the quadrupole will vary as a function of its trapping well depth. So that means that after the quadrupole component, the intensities of the ions may not be the same anymore. They may have been restricted by the sensitivity of the quadrupole they passed through. So that may mean you see the most sensitivity for ions that had a Q of 0.6, but much less sensitivity for ions of higher and lower values of Q, like this. Now remember, Q is inversely proportional to the mass to charge ratio, so we can convert this Q value to the underlying mass to charge ratio values. And this biasing effect on the ion intensities is solely a function of the fact that the ion beam has passed through a quadrupole component. So just because in a mass spectrum you see lower intensities of very high mass ions compared to lower mass ions, that may not necessarily solely be because there was actually fewer of those components in the original sample. This may be an artifact of the fact that your ion beam has passed through one or multiple quadrupole components in the instrument before being detected. And this effect can be seen whether we're using our linear quadrupole as an RF-only ion guide or as the central section of a linear ion trap. In a linear ion trap, the probability of an ion produced outside the ion trap being trapped inside the ion trap is also a function of the trapping well depth. If the incoming ion beam includes ions with kinetic energies greater than the trapping well depth, then these will be lost instead of being trapped for analysis. For a given setup of linear ion trap, it will be most sensitive for ions that trap in the deepest part of the trapping well. And this means it will prove to be less sensitive for ions of much higher mass-to-charge ratios, as these will plot at lower values of Q and so experience a shallower trapping well. Therefore, if you find you need to improve the sensitivity for some high mass-to-charge ions, one strategy for doing this is to increase the RF amplitude. Because Q is proportional to V, as you increase V, you increase Q, so you can bring these high mass-to-charge ions into a deeper part of the trapping well. Of course, it's no good doing that for ions that are already trapped, because the sensitivity is locked in by that point. But the next time you fill the trap, you'll now be filling those high mass-to-charge ions into a deeper trapping well, so your sensitivity will improve. But now let's think about the ions that were a lower mass-to-charge ratio, that were originally in this region of the diagram. So let's see what happens to this lower mass-to-charge ratio ion as we move this heavier mass-to-charge ratio ion down to the bottom of the trapping well. As we increase the RF amplitude, the Q of both ions will increase by the same amount. But while the trapping well depth for the higher mass-to-charge ratio ion is increasing, it is decreasing for the lower mass-to-charge ratio ion, and at the boundary it drops to 0 and the ion is lost from the trap. And that should tell us that if we have an ion trapped at the bottom of the trapping well at a Q of 0.6, there's a relatively limited range of mass-to-charge ratios that are lighter than this ion that we can trap in that ion trap. And the lightest mass-to-charge ratio you can trap in an ion trap for a given setup is known as the low mass cutoff. And let's look at how we calculate that. So let's start with the basic equation for Q. For the first step, let's move the mass-to-charge ratio of the ion to the other side of the equation. So we multiply both sides by the mass and divide by the charge. And if we do that, the equation will look like this. Now for all ions that are inside a quadrupole ion guide or linear ion trap at the same instant, they're all experiencing exactly the same RF amplitude and frequency, and they're all inside the same quadrupole radius. So this right-hand side of the equation must be constant for all ions. And that means if we know the mass-to-charge ratio and Q value for one ion, we can work out the Q value for another ion if we know the mass-to-charge of that. And there's one last thing to note. For the normal Q equation, you have to use SI units for all variables. So that's coulombs for charge, V for volts, kilograms for mass, etc. But this last equation is an equivalence of two ratios. So now it doesn't matter what units we use for mass and charge as long as they're the same on both sides of the equation. So we can use Daltons for mass and the normal integer version of charge for Z. So now let's look at an example of using that equation for real. Let's imagine we have a linear ion trap and we've set its tune mass to 500, which means the ion of mass to charge 500 will be sitting at a Q of about 0.6. Under those conditions, what's the lowest mass to charge ratio that we can trap in that ion trap at that time? You need to know that the value of Q at the boundary is 0.908. So to go through the working on that answer, we know that the mass to charge ratio of ion 1 is 500 and its Q is 0.6. And we know the Q at the boundary is 0.908. So all we then have to do is rearrange the equation to solve for the mass-to-charge ratio of the second ion. And that gives us the result 330.396, but of course we have to restrict this to 3 significant figures because of the input numbers, and that gives us a result of 330. But now, let's imagine a situation where in our initial mass spectrum we have the ion of mass to charge 500 at a Q of 0.6 that we already discussed. But what if we also have an ion of mass to charge 3000, which will therefore have a Q of 0.1? Now you can see that the trapping well depth for this new ion is much, much lower. So if we want to boost the sensitivity, what will we do? As we discussed earlier, one of our options is to try to increase the Q value for that ion by increasing the RF amplitude. That's the V term in the Q equation. But if you remember, that means the Q of all ions will increase by the same amount. So some of the ions that were originally stable will now fall out the top end of the stability diagram. So now we have an ion of mass to charge 3000 at a Q of 0.6. So what's the low mass cutoff now? So the low mass cutoff now is 1980. So you have a combination of two effects. If you're using a linear ion trap as your mass analyzer, or your ions are passing through a quadrupole ion guide on the way to a second mass analyzer, you may not be able to see the full mass spectral range you need with a single quadrupole setup. Below the low mass cutoff, you simply won't see any ions at all. But if you set the quadrupole tune mass too low so that you have a good low mass cutoff, then your sensitivity for high mass ions will be very poor. And that's why in real instruments, the mass spectrum you see may not actually be a single mass spectrum. Many instruments get around this low mass cutoff and high mass sensitivity issue by actually running two scans. First, they run a low mass scan, where the quadrupole tune mass is set to a low value, and that will give you therefore a low mass cutoff. Then they also run a high mass scan, where the quadrupole tune mass is set to a much higher value in order to boost the sensitivity for high mass ions. Then they combine these two spectra together to show you a single mass spectral output that has both a low mass cutoff and good sensitivity for high mass ions. "3D ion traps also show the same low mass cutoff effect that linear ion traps do. And of course, remember, 3D ion traps need to use their own Matthew equations and they have their own stability diagram. But conveniently, the top end of their stability diagram still crosses the Q-axis at 0.908. And if you rearrange the 3D ion trap Q equation, you end up with the same ratio relationship as you did for the 2D ion traps. So you can calculate the low mass cutoff for 3D ion traps in exactly the same way as you do for 2D ion traps. We're now going to look at a specific implication of the low mass cutoff when it comes to tandem mass spectrometry. And we'll discuss it as it pertains to the 3D ion trap. But exactly the same effect will also be evident when you're using 2D linear ion traps. It's just then you have to use the linear ion trap Matthew equation and the linear ion trap stability diagram. So in the next session we're going to focus on tandem mass spectrometry as a concept, but for now let's look at this specific issue. The steps in tandem mass spectrometry are that first of all you isolate an ion of a particular mass to charge ratio, then you fragment it, and then you analyse the mass to charge ratios of the fragments. But the instant the fragment ions are formed, they will be in the same RF amplitude, frequency and quadrupole radius conditions that the parent ion was in. And it's quite common for many of the fragments to appear in the spectrum at a lower mass to charge ratio than the parent ion. Now, because of the inverse relationship between Q and the mass to charge ratio, ions of lower mass to charge will appear at higher values of Q. Now, fragmentation in a linear ion trap generally happens when there's no DC offset, so all the ions will be on the Q axis. So that means the top edge of the stability boundary is at a Q value of 0.908. If you produce, as a result of the fragmentation, fragment ions that have a mass-to-charge ratio which would give them a Q greater than 0.908, then they will not be trapped in the ion trap and you will not be able to see them in the resulting mass spectrum. So when setting up a tandem mass spectrometry experiment in an ion trap, either 3D or linear, it's important to consider this low mass cutoff issue. Under the circumstances where you have a particularly important fragment ion, but it will commonly appear at some mass-to-charge range lighter than the parent ion, then it's important to consider whether or not it's going to be within the low mass cutoff of the experimental setup you're using. So here's an example question for you to think about. Nandrolone is an anabolic steroid which is on the banned list for athletes. Several well-known athletes have been sanctioned for its misuse, and indeed some were even imprisoned for lying about it. Tandem mass spectrometry is one of the key ways of confirming the presence of nandrolone in a sample from an athlete. For the purposes of this question, let's assume that you need to be able to detect all the fragment ions shown here on this page. If the parent ion, that's the complete molecule, was originally trapped at a Q of 0.3, which fragments will still be trapped after fragmentation? Put ticks in the boxes next to all the fragments you think will be detected, then hit submit. So the fact that the trapping well depth varies as a function of Q in quadrupole ion guides, quadrupole ion traps, and linear ion traps is a form of mass bias. And here, mass bias means that in the final mass spectrum, the signals corresponding to the ions will have been modified by their interactions with the quadrupole-based components that they encountered on their way to the detector. But that modification won't have been constant for all ions, and will have varied as a function of their mass-to-charge ratios. So, purely as a consequence of their mass-to-charge ratios, the intensities of some ions may have been reduced, while others below the low mass cutoff may have been removed entirely. And so that's the first mass bias associated with use of quadrupoles. The second mass bias affects quadrupoles when they're used as mass filters, so we'll go on to look at that one now too. In order to record a mass spectrum in a quadrupole mass filter, we undertake a process known as ramping or scanning the RF. And during the RF scan, the voltages go from low to high. And so the corresponding voltages being sent to the quadrupole rods look like this. For both the X and the Y rods, the voltage amplitude and DC offset increase linearly during the length of the scan. So now let's recall what effect this has on ions in the stability diagram. Here are the ions on the scan line at the beginning of the ramp. Now, as we scan the RF, because the A value for every ion is proportional to U, the DC offset, and the Q value for every ion is proportional to V, the RF amplitude, as we increase these together, ions appear to slide up the scan line. So now let's look at that again, but this time think about what signal will be seen on a detector at the far end of the quadrupole. At the beginning of the ramp, all the ions are outside the stable region, so there'll be no ions hitting the detector. Then, as we increase the ramp, one after the other, the ions pass through the stable region at the tip of the diagram, and so we'll end up getting 4 distinct peaks on the detector at different times during the ramp. But one aspect of this operation that we didn't think about before is the width of the peaks. During the mass scan, we'll see signal corresponding to an ion as long as that ion is inside the stable region at the tip of the diagram. So let's go and look at how the mass-to-charge ratio affects that. But we can't really see the detail that's going on at the tip of the stability diagram just now, so as a first step we'll need to zoom in on that. So here, right at the tip of the stability diagram, you can see that the region of the scan line that's inside the stable region is defined by a small range of Q and A values. And in the same way that we could use rearrangements of the Matthew equations to help us calculate the low mass cutoff in quadrupoles, we can do the same approach here in order to calculate the mass range that's within the stable region at any given time. We could actually do this calculation with either the A or the Q Matthew equation, but as we use the Q1 for the low mass cutoff, we'll use the A1 for this task. So just like the derivation for the low mass cutoff equation, in this case if we move the mass to charge ratio of the ion onto the left hand side, what we're left with on the right hand side should be a constant for all ions in that quadrupole at that time. So that means that the A value times the mass to charge for one ion should equal the A value times the mass to charge for another ion in the same quadrupole. So let's assume that for a particular scanline setup, these two values of A define the extent of the part of the scanline that's inside the stable region. So then, if the lowest stable mass to charge was 100, what would the mass to charge at the top end of the peak be? So having calculated that value, now you should be able to work out what the width of the peak will be at the baseline. And now I want you to consider what the width of the peak would be if the lowest stable mass was 1000 instead of 100. So what this means is that when you're running quadrupoles as a mass filter, the spectral peak width will be proportional to the mass to charge ratio. So the heavier an ion you look at, the wider the peaks will be. And yes, the resolution, that's the mass divided by the delta mass, is constant across the spectrum, but the peak width is not. It gets larger with mass. So whilst you might be able to see the isotopic peaks fully resolved for low mass ions, beyond a certain mass you won't be able to see that anymore. And if you go high enough up in mass, all the isotopic peaks will blend into a single distribution. But what if you need to have the isotopic peaks fully resolved for a high mass ion? What can you do then? Well, the answer is, of course, you increase the angle of the scanline so that you're in a narrower part of the tip of the stability diagram. But as we discussed last week, as you get closer to the tip of the stability diagram, the quadrupole trapping well depth decreases, and that means the sensitivity will also decrease. So if you want to keep your resolution high for high mass ions, that means you're going to have to accept lower sensitivity. So the second mass bias effect in quadrupoles is that as mass increases, you either lose sensitivity or resolution, or you have to make some compromise between the two. In the first quadrupole session, I recommended having a look at some of the guides that Ardara Technologies have put on their website. And that still holds true now, so if you haven't gone through those already, now would be a good time to do it. The next thing I want to look at is what are known as RF-only pre-filters, or Brubaker filters, or stubbies. Here are the internal components of an old triple quad instrument that we have in the lab. We'll cover what triple quads are in the last lecture, but just now let's just focus on this first quadrupole. Hopefully you can see what appears to be a small break in the quadrupole rods just after the inlet. And there's a similar break at the exit end of the quadrupole, where again there's a small set of quadrupole rods just beyond the break. So in this section we're going to look at why quadrupoles are often designed this way. So to understand this, let's think about how an ion gets into a quadrupole mass filter. Here's a really simple schematic showing how a basic single quadrupole instrument might work. Let's imagine that ions are produced over here, and those ions then have to get through the quadrupole and to the detector to generate a signal. In this example, before the ions get to the quadrupole, they pass through this metal plate with a small orifice in the middle of it, which is held at a ground potential. So, as an ion passes through that orifice, it sees a potential of 0 volts. And that means from the point of view of any quadrupole voltages, it's plotting at A equals 0 and Q equals 0 on the stability diagram because it's seeing no DC offset and no RF amplitude. Now let's imagine we're running this quadrupole as a mass filter. So that means that when the ion is inside the quadrupole, it needs to be right up at the tip of the stability diagram. But it can't magically jump up to those values of U and V. It has to get there gradually. So as this ion crosses the space between the ground plate and the quadrupole, it will see both the DC offset and the RF amplitude grow linearly. But now, if we look at what that means in terms of the stability diagram, see how the ion has to traverse all this unstable region before it sees the full voltages of the quadrupole, where it will plot inside the stable region at the tip. In fact, the ion doesn't see the full quadrupole fields until it's several times the quadrupole radius inside the quadrupole. And up until that point, all the way from the ground plate to that distance inside the quadrupole, it's in an unstable part of the quadrupole stability diagram. Once the ion sees the full quadrupole fields, the pseudopotential well helps constrain the ions within the quadrupole. But whilst it's in the fringe field region, in these unstable parts of the stability diagram, the ion beam's actually being defocused instead of focused. So if we actually constructed a quadrupole instrument like this, we'd expect to see a significant loss of the incoming ions as they got into the quadrupole, and that would translate into a loss of sensitivity. This fringe field effect of reducing the sensitivity of quadrupoles was well known early in the development of quadrupole mass analyzers. And a solution was relatively quickly identified by a guy called Wilson Brubaker working for the Bell Company. It's because they're his invention that these are still sometimes called Brubaker filters. His idea was to make the front end of a quadrupole RF only. The main part of the quadrupole still sees the full RF and DC voltages that we'll need to run it as a quadrupole mass filter, but the front section only sees the radio frequency component of the voltages. And the way this is achieved is to connect the two different parts of the quadrupole together via capacitors. These capacitors let the alternating part of the signal through, but block the DC component. So let's look and see how this Brubaker filter will stop the ion going through the unstable region of the stability diagram as it enters the quadrupole. So let's look at what voltages this ion sees as it moves from its original black position, through the blue position in the Brubaker filter, to the red position where it's seeing the full quadrupole potentials. Just like in the earlier example, when the ion is in the middle of the orifice in the ground plate, it sees 0 DC offset and 0 RF amplitude, so it plots at an A and Q of 0 at the origin of the stability diagram. Now, because the Brubaker filter only has the RF voltage applied to it, as the ion moves inside that, the RF amplitude increases, so Q increases, but there's no DC offset, so the A value remains at 0, and the ion tracks along the Q axis. Now, as the ion transfers from the Brubaker filter to the main quadrupole, it also sees the DC potential rise as well. So now if we look at how the voltages changed as the ion entered the quadrupole, we can see that it stays inside the stable region through the entire transition. And that's why adding these Brubaker filters, RF only pre-filters, or stubbies, improves the sensitivity of quadrupoles. The quadrupole fringe fields don't just have a defocusing effect on an ion beam as ions enter a quadrupole, they'd also have that same effect as ions left a quadrupole. So if we want to get ions out of a quadrupole and then pass them on to some other part of a mass spectrometer, we don't want to lose ions there either. So in real instruments, like that triple quad I showed at the beginning, they often have these Brubaker filters or stubbies at both ends of the quadrupole to stop defocusing on the way in and also to stop defocusing on the way out. In this section, we're going to look at how you generate mass spectra from ions trapped in ion traps. In a previous session, we looked at how the ion oscillation frequency varied depending on where you were in the stability diagram. In a perfect quadrupolar field, you can consider the ion motion in the x direction and the ion motion in the y direction completely separately. So using that long irrational fraction, or by the ion modelling method, we could determine the ion oscillation frequency in both the x and the y direction for an ion at any point within the stability diagram. And so while the ion oscillation frequency is a function of A, Q, and beta, it's not a function of the mass-to-charge ratio. Any ion plotting at the same A and Q coordinates will have the same frequency, relative to the quadrupole drive frequency, irrespective of what the mass of that ion is. And this is an important thing to remember for the description we're about to go through. Now let's look at what happens when we apply the same approach to the quadrupole ion trap stability diagram. But remember that for 3D ion traps, AR equals minus 2 times AZ, and QR equals 2 times QZ. And this relationship will have the effect of stretching all the isobeta lines for the radial direction, not just those that form the boundaries of the stability region. And that means when an ion reaches this boundary here, it's still stable in the radial direction, it only goes unstable in the axial direction. When collecting mass spectra from quadrupole ion traps, they're normally run in RF-only mode, so there's no U or DC offset, and that means all the ions plot on the Q-axis. For this example, you can see we've got 3 ions trapped within our ion trap. We've got a heavy red ion, a medium weight orange ion, and the blue ion is the lightest. To begin with, they're all in the middle of the stability region. In order to collect a mass spectrum, what we're going to do is ramp the RF, which means continuously increase the RF amplitude. Because Q is proportional to the RF amplitude, as we ramp the RF, the Q value for all the ions will increase at the same time. So let's start this RF ramp and see what happens. As a consequence of the RF ramp, the Q value of all ions has increased until now the blue ion is on the stability boundary. And remember, this is the axial stability boundary, so when the ion crosses it, it will go unstable in the axial direction and fly off to hit the electrode. But if you look up here, you can see there's a hole drilled in the electrode. So what actually happens is the ion passes right through the electrode and out to hit the detector. And so we see a peak in the spectrum. And all the time the RF amplitude is still ramping, so the Q values of all the other ions continue to increase as well. And as with the blue ion, the orange ion now also becomes unstable in the axial direction, and so flies out through the hole in the end cap to hit the detector and produce the second peak in the spectrum. And finally the RF ramp will increase until the red ion also reaches the boundary, becomes unstable in the axial direction, and flies out to hit the detector and so produce the third peak in the spectrum. So that's the basics of a process known as boundary ejection, which is one possible way of producing a mass spectrum from ions in an ion trap. But although I've gone through it slowly, it's not actually the method used in commercial ion traps. That method is called resonant ejection, so now we'll explain how that works. Let's consider the example of ions in a 2D ion trap. Now to collect a spectrum of these ions, we'll apply the same approach that we did in a 3D ion trap. We'll ramp the RF so that the ions are moved up in Q until they reach the stability boundary. Now at this point the blue ion became unstable in the axial direction in the quadrupole ion trap, but in the linear ion trap you can see it's actually going unstable in both the X and the Y directions simultaneously. So then we'd have to fit detectors in both directions. But there is a way we can force the ion to be ejected only in one of the two possible directions. Remember that the ion oscillation frequency varies as the ion is moved around within the stability diagram. If we know the A and Q values that an ion has, we can predict using that long irrational function what the beta value is, and therefore what the ion oscillation frequency will be at those A and Q coordinates. So let's choose the A and Q coordinates, which would give us a beta value of 0.8. If beta is 0.8, then that means the ion secular frequency must be 0.4 times the quadrupole drive frequency. So if, in our imaginary linear ion trap, the RF drive frequency was 800 kHz, That means the ion secular frequency for an ion at this beta would be 320 kHz. In our imaginary linear ion trap, both the X and the Y rods will already have the 800 kHz quadrupole drive frequency being sent to them. But now, if we add an extra signal only onto the X rods, and where this extra signal has a frequency of 320 kHz, when ions reach a beta value of 0.8, they'll be resonantly excited by this signal and ejected only in the X direction. And we can plot this extra signal like an iso-beta line on the stability diagrams. This extra signal is also called the tickle signal or tickle voltage, and it's used in both commercial linear ion traps and quadrupole ion traps. In linear ion traps, this tickle voltage is applied to the X rods, but not the Y rods. And in quadrupole ion traps, it's applied to the N caps. So when collecting spectra in this resonance ejection mode, a similar process is used in both linear and quadrupole ion traps. The ions start somewhere in the middle of the stability diagram. Then, as the RF voltage is ramped, the Q values of all ions increase. As the Q values of the ions increase, so does their beta value, and therefore so does their oscillation frequency. When the oscillation frequency of the lightest ion rises to match that of the tickle voltage, it becomes resonantly excited out of the pseudopotential well of the ion trap and into the detector. And then, as each subsequent ion also reaches that resonant frequency, they too get ejected out of the trap and into the detector. So in this mode of operation, ions never reach the boundary of the stability region. Now there are two key benefits to this resonant ejection approach. The first one of these affects only linear ion traps. As we said earlier, if we didn't use this approach, when ions reach the boundary of the stability region in a linear ion trap, they would become unstable in both the X and the Y directions at the same time, and so we'd have to have detectors on both axes. By using the resonance ejection approach, however, we now only need to detect ions in the X direction. And that's why, if you look in the central section of a linear ion trap, you'll find there's a slot cut in one pair of the rods. These will be the X rods. And just like the holes in the end caps of an ion trap, the slots in the X rods in a linear ion trap are there to let the ions be resonantly excited out of the trap and onto the detectors. As a result of this resonant excitation, we know the ions are going to go unstable in the X direction, but there are two X rods and it could come out of either one. So to maximize your ability to detect ions coming out of an ion trap like this, you need to have detectors on both sides, not just on one side. So to recap, the first benefit of using resonance ejection in ion traps affects only linear ion traps. By putting the extra tickle signal only on the X rods, we guarantee that those are the rods that the ions will be ejected through. The second benefit of resonant ejection affects both kinds of ion trap. In order to visualize this benefit, we need to go back to looking at the potential well that ions see as they're trapped in an ion trap. In this view, the horizontal axis is Q, and the vertical axis is the trapping well depth. The trapping well depth drops to 0 when we get to the boundary of the stability diagram, and that's at a Q value of 0.908. If the ions in the ion trap had no temperature of their own, then they wouldn't leave the ion trap until the well depth dropped to 0. And under those circumstances, we'd get very good spectral resolution. But in real life, the ion cloud will have a temperature. What this means is that some of the ions of a given mass and therefore a given Q value will sit as deep in the energy well as they can, but other ions will start slightly higher up. They'll be nearer the edge of the trapping well. Now, as we run the RF ramp, both of these ions, remember with the same mass to charge ratio, will move together towards the boundary. But now you can see that some of these ions have enough energy to escape from the ion trap before they get to the boundary. And that means the ions in this ion packet are beginning to leak out of the ion trap and be detected earlier than they should be. And that means that if we use the boundary ejection method as a way of collecting mass spectra from ion traps, we'll end up with much broader peaks than we would like to see. But when we add our resonant ejection tickle signal onto our ion trap, either the end caps in a quadrupole ion trap or the X rods in a linear ion trap, the trapping well depth profile changes to look like this. This sharp loss of the trapping well depth is a result of the resonant excitation of ions at that value of Q. And because it has such sharp edges, that's why all the ions of a given mass to charge ratio will be ejected from the ion trap at approximately the same time, irrespective of their energy spread. And that's why the second benefit of resonant ejection is improved mass spectral resolution. And that's true for both linear ion traps and quadrupole ion traps. And it's for that reason that all commercial ion traps use a resonant ejection method. The method of resonant ejection that I've just explained to you for linear ion traps is one of two commercially available methods. It's known as the radial ejection method, so the ions are exiting radially through slits in the rods. And this is the method of resonant ejection used in thermolinear ion traps. The other most common manufacturer of linear ion trap mass spectrometers is SciEx. Their system uses a different method of axial radial ejection, where ions come out the end of the linear ion trap. On this slide, I've added links to the papers that describe both of these competing methods, so you should download them both, read them, and see if you can identify what the differences are between the thermo and the SciEx methods of ejection. The key thing to remember though is that in thermolinear ion traps, the ions are being ejected radially through slits in the rods to detectors on either side of the linear ion trap, whereas in SciEx instruments they're being ejected axially to a detector at the far end of the linear ion trap. The last thing I want to go through in this session is an explanation of how you can do MS/MS in ion traps. Now I'm going to be using 3D ion traps as the example in this section, but everything I'm going to say for 3D ion traps is also true for 2D ion traps. It's just for those you have to use the quadrupole stability diagram, not the 3D ion trap one. So there are three stages in any MS/MS experiment. First of all, we've got to isolate our ion of interest, then we have to find a way of fragmenting that, and then we can analyse the fragments. There are two options for isolating ions of interest in ion traps. The first method is called apex isolation, and the second method will group under the general category SWIFT, and I'll cover what that is in a minute. But first, let's go through the concept of apex isolation. Normally, when you're running a mass spectrum in an ion trap, there's no DC offset, so the ions all sit on the Q-axis, like I'm showing here. But when you want to use apex isolation, you add a DC offset, and that means the ions will plot on a scan line like they did when we were using a quadrupole mass filter. Then the ion trap will set the RF and DC voltages such that the ion that you're interested in stays in the tip of the stability diagram, while the other ions in the trap are in unstable regions and are lost. Then, having isolated the ion of interest, the external voltages are removed and the ion can be brought back down onto the Q-axis. So now we've successfully isolated just the orange ion in this ion trap. The second method of isolation relies on the fact that ions of different mass to charge ratios oscillate inside the ion trap with different frequencies. Remember that if we apply a tickle frequency that is the same as the ion oscillation frequency, we can eject that ion from the ion trap wherever it is in the stability diagram. We don't have to wait until it gets to a boundary. So if we knew the oscillation frequency of any of these ions, we could eject them straight from the trap just by applying the right tickle frequency. But then if you didn't know exactly what ions were in your ion trap at any one time, you wouldn't know what frequencies to create. So let's turn the whole idea on its head. If we know the oscillation frequency of the ion we want to keep in the ion trap, well, why don't we create all the other frequencies except that one, and that will guarantee we eject all the ions except the ones we want. SWIFT stands for Stored Waveform Inverse Fourier Transform. You can use normal Fourier transform to take a sinusoidal time-based signal and identify what frequencies are in it. Inverse Fourier transform is the opposite process. You feed a list of frequencies and amplitudes into an inverse Fourier transform, and what you get out is an oscillating time-based signal containing all those frequencies. We know that the ions trapped in an ion trap will have a frequency somewhere between 0 and exactly half the drive frequency. So we can use this inverse Fourier transform approach to generate a waveform that contains the frequencies of all possible ions except for the ion that we're interested in keeping in the ion trap. So when we trap ions in the ion trap, that signal is off. But when we want to isolate our ion of interest, we turn it on, eject all the other ions resonantly from the ion trap, leaving us only with the ion we want, and then we can turn the SWIFT signal off again. In science circles, an in-depth knowledge of SWIFT is known to be a powerful aphrodisiac, so I strongly recommend reading the paper I've linked below. But whether you've used apex isolation or SWIFT, by this point you'll have a single ion of interest isolated in your ion trap. And now you've isolated your ion of interest, the next thing we have to do is fragment it. So to cause fragmentation of ions in ion traps, we apply a tickle voltage as if we were going to eject it from the ion trap, but where the amplitude of the tickle voltage is low enough that the ion gets excited within the trapping well, but doesn't get enough energy to escape out of it. But that does mean that its collisions with the background gas molecules are at a much higher energy than they would have been before we'd excited it. So the internal energy of the ion slowly builds up until the weakest bonds fragment. And this is known as collisionally induced or collisionally activated dissociation. There are other methods of fragmenting ions in ion traps, but CID is by far the most common. Now when you're undertaking CID in an ion trap, the low mass cutoff is one of the things you need to consider. If you're making ions which are much lighter than the parent ion, then are these still going to be trapped in the ion trap for you to detect afterwards? If not, then you need to change the Q value of the parent ion, pull it towards the origin, which gives you more space for lower mass ions to be trapped. Assuming your fragment ions are trapped in the ion trap, then you can collect a mass spectrum of those by using an RF ramp, the same as we explained earlier. Alternatively, if you need more in-depth structural information about a molecule, you can choose to isolate one of these fragments, and then fragment that into more fragments, isolate one of them, fragment them, and so on, until you get a deeper and deeper structural understanding of the analyte you're looking at. This process is called MS to the N, and we'll come on to that in a later session. But that brings us to the end of this last session on quadrupoles and ion traps. So here are some questions you might like to think about to check that you've understood the contents. In quadrupole mass filters, which ions are closest to the origin of the Matthew stability diagram? And can you remember what causes both types of mass bias? In 3D ion traps, if the molecular ion of estrogen is at mass to charge 296 and is fragmented when it's at a Q of 0.25, what will be the lightest fragment mass to charge you'll expect to see in the mass spectrum? And why do you run ion traps at a poor vacuum? Why do ions get ejected from ion traps when they reach the boundary of the stability diagram? Can you describe two different methods of isolating a specific mass to charge in an ion trap mass analyzer? Can you remember why quadrupole mass filter instruments are often fitted with RF-only pre-filters? And can you remember the other names for these? And can you remember why resonant ejection improves the mass resolution in ion traps? Here are some last things to think about. Can you say what a tickle voltage or tickle frequency is? Can you remember how a tickle voltage will affect ion motion in an ion trap or linear ion trap? And with the aid of diagrams, would you be able to explain how a linear ion trap can generate a mass spectrum? I've also made an HTML5 version of this video. The benefit of watching the presentation in HTML5 mode is that you get to go through it at your own pace and answer questions and problems as you go along to help you understand the material. To find the HTML5 versions, go to the Kilgour Lab website at www.kilgourlab.com and then go to the Teaching Resources page. On there you'll find a whole variety of resources to help you learn about mass spectrometry. I hope you enjoy them. And that brings us to the end of this third and final section on quadrupoles and ion traps. Remember, with great power comes great responsibility. The aphrodisiac qualities of knowledge of Swift are extremely powerful, so please use them with care and caution.